Swayam Prabha. Digital India. Educated India.
Welcome to the 12th week. This week we will start with the discussion of flow mode analysis, but instead of using the Bingham plastic model that we did before, here we will use Herschel-Berkeley fluid model. Now, as per the Herschel-Berkeley fluid model, as we have seen before that, this fluid model is nonlinear. So, the post yield behavior is modeled using a nonlinear equation. So, the model looks like this. After the yield point, the shear stress versus shear strain graph looks like this. So, this is our tau y and this we can say minus tau y. So, the equation is tau equal to tau y plus k multiplied by gamma dot to the power n. And this is when our gamma dot is greater than 0, which means this part of the graph, the upper part, the positive part of the graph. And then we have tau equal to minus tau y plus k gamma dot to the power n, and this is when our gamma dot is negative. Now, here we have to be careful. So, it is better that we put a mod sign here and put a negative sign here. So, that makes the graph same as the graph at the negative side, same as at the positive side. Now, here this entire thing is post yield behavior. And this graph here we have n greater than 1. So, that is why we can see that when increase in gamma dot, the slope of the graph is also increasing, which means the viscosity is increasing with gamma dot, and this is called shear thickening behavior. If I draw the graph tau versus gamma dot here with n less than 1, then the graph looks like this. And here it is n minus 1. So, it is shear thinning behavior. So, the effective viscosity is reducing as the shear strain rate is increasing. Now, in general the ER or MR fluids are shear thinning fluid, which means in most of the cases they have n less than 1. But in our formulation is more generic here, whether it is greater than or 1 or less than 1 does not matter, the same formulation holds. So, we will do it using the flow mode. So, in the flow mode, as we have seen before, we have two plates, there is upper plate and there is a lower plate, and both the plates are fixed, and in between them the velocity varies. Now, we have seen that there is a region in between, around the midline of it, there is a region where the fluid behaves like a solid, in the sense that there is no velocity gradient in this region, and that we call as plug, and from here to here the distance we denote as y1, and from here to here the distance we denote as y2. And we have seen that, and this distance between these two plates we can denote that as d. This is our x axis and this is our y axis, and we have seen that our y1 is d minus delta by 2 and y 2 is d plus delta by 2. The velocity varies here from y equal to 0 to y equal to y n, and again from y 1, and again from y equal to y 1 to y equal to d, and in between y equal to y 1 and y equal to y 2 the velocity is constant. This is when the field is in the flow is in active mode. So, here we will do active mode analysis only. That means, our tau y is non-zero, there is non-zero yield stress because of non-zero field that is applied. So, we will start with the governing differential equation, and the governing differential equation is del tau by del y is minus del p by L, and our constitutive relation we have written tau equal to tau y plus k del u by del y to the power n. Now, here, so if we substitute the governing differential equation, the equation of motion becomes del by del y k del u by del y n equal to minus del p by L, and then if we integrate the equation. So, this is obtained just by putting this here, and then if we integrate the equation, we get a equation of the form which is del u by del y to the power n minus del p by L k y plus C 1. Actually, if we integrate it, we get minus del p by L plus C 1 first, and then we divide by k. So, C 1 also gets divided by k, but because C 1 is a constant, we can absorb that k within C 1. So, we can write it in this form, and then after that from here we can find out the root of it, and we get del u by del y. And then that gives us minus del p by k L y plus C 1 to the power 1 by n, and then from here again after integrating we get minus del p by k L y plus C 1 to the power 1 by n plus 1, and this quantity also has to be divided by 1 by n plus 1. So, that gives us and then we have plus C 2. So, that is our expression for y. So, u as a function of y is this. After that our procedure is same. So, we find the we apply the boundary condition, and the boundary condition is velocity is 0 here. So, u equal to 0 here, we have u equal to 0, and we have del u by del y equal to 0, we have del u by del y equal to 0, and that gives us the velocity profiles. Then our next job is to find out the plug thickness that we get from the shear equation here. So, only thing is that because of the power n, the flow profile looks different. So, we put the boundary condition. Okay, now, before that, if we call this as region 1, we call this as region 2, and we call this as region 3. Now, we put the boundary condition. So, in region 1, our boundary conditions are that at y equal to 0, we have u equal to 0, or we can call it u 1 equal to 0. So, u1 means u at region 1, and then we have at y equal to y1 the velocity gradient is 0. So, we can say del u by del y equal to 0. This we also write as del u 1 by del y, because in region 1 u is just u 1. So, the first boundary condition gives us, if we put everything, if we put these boundary conditions, satisfy the boundary conditions, then the first boundary condition gives us C 1 equal to delta p divided by k L multiplied by y 1, and then we get C 2 equal to n by n plus 1 delta p divided by k L to the power 1 by n into y 1 to the power n 1 plus 1 by n. So, these are the two constants that are evaluated after applying the boundary condition. So, after evaluating the constants, we can put them in the governing differential equation, in the equation for u, and that gives us the velocity profile. So, velocity profile in region 1 looks like this: u 1 as a function of y becomes minus n by n plus 1 into delta p k L to the power 1 by n multiplied by y 1 minus y n plus 1 by n minus y 1 into n plus 1 by n. So, that is our velocity profile in region 1. So, we can see here that if our n is equal to 1, then it becomes a quadratic equation of y. Here, depending on the n, the degree would change. Next, we have to go to region 3. So, region 3 is the uppermost region. So, if we look here, now the flow profile, whatever we see the flow profile here, that is symmetrically can be seen in region 3 also. So, just by using the symmetry we can find out the flow profile here. Now, please understand the velocity gradient in region 3 is negative. So, just by using symmetry we can say that u 3 y is equal to u 1 d minus y. So, u 3 is the velocity profile in our region 3. So, this comes from symmetry. Symmetry of flow profile or velocity profile. Now, if that is so, then our expression for u 3 is minus n by n plus 1 into delta p by k L to the power 1 by n multiplied by y minus y 2 to the power n plus 1 by n minus d minus y 2 to the power n plus 1 by n. So, these two profiles here, this and this, they are symmetric with respect to the midline. Now, we need to go to region 3. Sorry, we need to go to region 2. We have already evaluated 1 and 3. Mid region is region 2 and that is our plug region. So, in region 2, first we find out the velocity profile, and again if we go back to the figure, whatever the velocity here, the same velocity is here and that velocity is same within that entire plug region. So, if we evaluate the velocity here by using the expression of u1, and if we evaluate the velocity here by using the expression of u3, we get these two velocities to be same, and that is the constant velocity that is maintained within that plug region. So, we can say that u2 as a function of y, which is eventually not a function of y, is equal to u1 evaluated at y is equal to u3 evaluated at y2. So, u1 evaluated at y1 is equal to u2 evaluated at y2. Now, if we do that evaluation, then the expression becomes n by n plus 1 multiplied by del p by k l to the power 1 by n multiplied by d minus delta 2 d minus delta by 2, which is our y 1 to the power n 1 plus n plus 1 by n, and that is the velocity at which the plug region moves. Now, we have to find out the thickness of the plug region, which means delta. So, evaluation of delta. So, for that also you will use the same approach that we used for the Bingham plastic model. Now, our equation is del tau 2 by del y is equal to minus of del p by del p by L, and then if we integrate the equation. So, tau 2 is the velocity in region 2. So, if we integrate the equation, it gives us tau 2 as a function of y is equal to minus del p by L y plus C 3. And then we know that at y equal to y 1, our yield stress is tau y and stress is tau y, and at y equal to y 2 the stress is minus tau y. If we go back to the image once again. So, here where the region 1 moves, the junction between region, where the region 1 ends, the junction between region 1 and 2, here our tau is equal to tau y, because here the velocity gradient is, I mean in region 1 the velocity is positive, velocity gradient is positive. So, here tau is equal to tau y. In region 3 the velocity gradient is negative. So, in between region 2 and region 3, that means at the upper end of the delta region, the plug region, tau is equal to minus tau y. If we put these two boundary conditions, that can help us find out the constants and the thickness of the plug region. So, at y equal to y 1, we have tau equal to tau y, and this gives us tau y, the yield stress is equal to minus del p by L into y 1 plus C 3, and then at y equal to y 3, we have tau equal to minus tau y, and that gives me this equation minus tau y equal to minus del p by L multiplied by y 2 plus C 3. Now, if we add these two equations, we can evaluate C3. So, adding these two equations, we get C3 as delta P by L multiplied by y1 plus y2 divided by 2, and we know that y1 plus y2 is d, the distance between the two plates. So, that gives us delta P d by 2L. Now, we can put this C3 in one of the equations, and that can help us evaluation of with the evaluation of delta, or we can subtract these two equations also, then C3 gets eliminated and delta can be evaluated, because our y1 and y2 both are linear function of delta. So, from that we can find out delta as tau y multiplied by 2L divided by delta P. So, we can see that the thickness delta is, as per this model, is same as the thickness delta that we got from the Bingham plastic model. So, same as that obtained using Bingham plastic model. Now that we have got tau, we can write the everything, and now that we have got delta. So, we have if we know delta, we know y1 and y2. So, accordingly we can write all the velocity profile and the shear profile properly. So, with that we can say that tau as a function of y becomes tau y plus delta P by L multiplied by y1 minus y, and then tau 2 y, tau in the region 2 is delta P by 2L d minus 2 y, and tau 3 as a function of y is minus tau y minus delta P by L y minus y2. So, our governing differential equation says that shear del tau by del y is equal to minus del P by L, and integrating that we get that our variation of tau along y is linear, and that is what we see here. So, if you want to plot the shear distribution, it would look like this. So, when y is equal to 0, our tau is tau y plus delta P by L into y1, which is like this, and when our tau is equal to d, then if we put d, we get the same shear, but with a negative sign. So, if you put y equal to d here, it becomes d minus y2, and d minus y2 as we know is equal to y. So, the shear here and shear here are same, but opposite, and in between them it varies linearly. So, at d by 2 the shear is 0, shear stress we are talking about here, and it is this. So, here it is tau y plus delta P by L multiplied by y1, and this value is also tau y plus delta P by L y1. Here it is 0, we have some plug thickness delta, and so this amount is delta and this entire amount is entire distance is d. And if we want to evaluate tau at y 1, so it is if we just put y equal to y 1, then this quantity becomes 0. So, tau 1 at y 1 is tau y, and here it is minus tau y. So, this quantity is minus tau y. So, this is plus and this is minus. Now, please understand tau y is not the location along y here, it is this dimension to be more specific. So, this is tau y and this quantity is tau y. Next, our goal is to find out the effective damping, and for that again we apply the same procedure. Our procedure is that we find out the total flow and then we equate that total flow to a flow which we would have obtained if I would have assumed an uniform flow throughout, and by equating that we get the equivalent uniform flow, and from that equivalent uniform flow we can find out the damping coefficient, we can find out the total force from the pressure, and then dividing that force by the equivalent uniform flow which we generally denote as UM, we can find out the damping coefficient. So, our total flow is here consists of the contribution from these three regions Q1, Q2 and Q3, and we know that the Q1 and Q2 are same. So, it becomes 2 Q1 and then we have Q2. So, if I add 2 Q1 plus Q2, that gives me total flow. So, here we do evaluation of damping coefficient. So, for that the total flow Q is Q1 plus Q2 plus Q3, which we write as 2 Q1 plus Q2 from the symmetry, and then we have 2 Q1 equal to B multiplied by 2 into 0 B multiplied by some quantities in a bracket, and then we have 2 multiplied by integral of u1 over 0 to y1, and we have integral of u2 over y1 to y2, and then we know that we can rewrite the expression in a better way. So, we have 2 multiplied by integral of this quantity over 0 to y1 and here we have B and y1 to y2 . Integral of this quantity, and finally, after doing all the integrations, the flow rate Q becomes B n multiplied by delta P by K L to the power 1 by n multiplied by d minus delta to the power n plus 1 by n multiplied by n into d plus delta plus d divided by 2 n plus 1 by n plus 1. So, this is our total flow rate Q. After that, from here we will find out the equivalent constant velocity, and from there we will find out the damping coefficient, and then we will find out the ratio of the damping coefficient in the active mode and in the inactive mode. So, we will do that in the next class. We will end this lecture here. Thank you.